Hello, welcome to our semiconductor education program. This is Vincent Chang. In this lecture, we're going to continue what we learned from the previous lecture, which is the LC tune oscillator, and to show you two types of LC tune oscillator. The first one is called the Hartley Oscillator. The second one is called Colpitts Oscillator. Hartley and Colpitts. This is what we learned from the previous lecture. LC tuned oscillator. So comparing with the model of a sinusoidal oscillator. So you see the blue part represents the basic amplified. The A represents the open loop transfer function. And then the purple one is so-called the frequency selective network. And the summary from the previous lectures tells us the frequency of oscillation is fully determined by the frequency selective network. It looks very simple, right? The sum of the three individual reactances equals 0. The three individual reactances equals 0. And the minimum gain to squat, minimum open loop gain to start the oscillation is the ratio of the two reactants. Let's say X1 divided by X2 is the minimum open loop gain. So now, the frequency selective network should be purely reactive. LC tuned oscillator, each component either inductive or capacitive. If you have, so you only have the two combination, right? Either you choose the two inductance with one capacitor, or two capacitors with one inductor. If it's the first one, the former, then it's called Hartley Oscillator. If it's the latter, it's called Colpitts Oscillator. So let me show you. The first type, this is the CMOS inverting amplifier connected with the LC tuned network. The first one shows you on the left-hand side shows you two inductors with one capacitor. This is called the Hartley Oscillator. If it's the two capacitors with one inductor, this is called a Colpitts Oscillator. So let's start with, so look at this again before we move on to the next slide. Two inductors, one capacitor, Hartley. Two capacitor, one inductor, it's called Colpitts. So for the Hartley oscillator, you are supposed to be very familiar with this, right? Basic amplifier and frequency selective network. From the Barkhausen phase criterion tells us, to meet the Barkhausen phase criterion, the sum of the three individual reactances should be 0. And then now it's time to plug in. What is X1? Omega L1. What is X2? Omega L2. What is X3? Negative 1 over omega C equals 0. At the frequency of oscillation, this condition should be met. Then this will give you the frequency of oscillation. Now I want you to take a closer look of this frequency of oscillation. This frequency oscillation satisfies so-called the Barkhausen phase criterion. So let's take a closer look of this by looking at the series combination of the two inductors. If I ask you, what's the equivalent inductance from a series combination of the two inductors? The answer is easy, right? Just add up. So LS represents the series combination of the two inductors. LS represents the equivalent series inductance. if I ask you, what's the resonant frequency for this LC network? LSC network. The answer is also easy. The 1 over square root of what? LS times C, like this. Right? You see the link? So I'm trying to link the frequency oscillation with the resonant frequency. So I already proved through the Barkhausen phase criterions, we got the so-called frequency of oscillation is actually equivalent to the resonant frequency of the LC network, right? The resonant frequency of the LC network. So now, let's move on to the Barkhausen magnitude criteria. Well, I already mentioned this. So if the minimum open loop gain is the ratio between x1 and x2, right? So you can cancel out the omega. So the answer is the L1 divided by L2. The ratio of the two inductors tells us the minimum open loop gain to start the oscillation, to ensure the oscillation will start, right? So this is the highlight, the total picture of the Hartley oscillator. So now let's move on to the Colpitts oscillator. So remember the Colpitts oscillator, the frequency selective network is composed by two capacitors and one inductor, right? Let's start with the Barkhausen phase criterion. The sum of the three individual reactances equals 0. X1, negative 1 over omega C1. X2, negative 1 over omega C2. X3, omega L. And adding these three up, you can solve the omega 0 is like this, the frequency of oscillation. So now, by the same token, as we did in the Hartley oscillator, I'm asking you to take a closer look of this frequency of oscillation. You'll find something interesting. If I were to ask you, what is the equivalent series capacitance? Equivalent series capacitance. Then you can take notes. It's the 1 divided by what? It's the sum of the inverse, and then you do another inverse, like this. Right? So this is the equivalent series capacitance. Then what is the resonant frequency? What is the resonant frequency? It's 1 over square root L, and then C what? CS. And if you plug the CS into this equation, you will see they are exactly the same. They are exactly the same. So the frequency of oscillation coming from Barkhausen phase criterion is equivalent to the resonant frequency of the LC network. As for the Barkhausen magnitude criterion, remember the x1 divided by x2, because the reactance of the inductance is inversely proportional to the capacitor. The reactance of a capacitance is inversely proportional to the capacitor's value. So for the capacitor, it becomes what? 2 divided by 1. That's the minimum gain to start a Colpitts oscillator. So here's the summary. The takeaway for the Hartley oscillator is this. It's very interesting to see the frequency of oscillation is the resonant frequency. They are equivalent to each other. The minimum gain to start the oscillation. And same thing with the Colpitts oscillator. It's also interesting to see this again. The frequency of oscillation is equivalent to the resonant frequency. So this is the summary for the LC-tuned oscillator. I hope you enjoy this lecture. Thanks for watching.